steric number of that carbon? 4. And this 4. And this one. That's also steric number 4. And this one. That's also steric number 4. Right? Why are these 4? 4 bonded atoms all around it, right? Why is this one a 4? Because it's got 2 bonded atoms and 2 lone pairs. Okay, so they're all steric number 4. So you can say all atoms have a tetrahedral electron geometry. Another thing we can say is that we can say all carbon atoms have tetrahedral molecular shape. What about the oxygen atom? What's the shape around that? That's going to be bent, right? Because it's a two bonded atom, 2 lone pair situation now. So we can say the O atom has a bent shape. You want to draw the VSEPR sketch?
No.
Oh, I know you want it. Okay, I know you want to. So we're going to do that. Okay, so let me just free up some space down here. Okay, so if this is a tetrahedral shape, how do we draw that? Well, it's going to get interesting. Check it out. You ever heard that there was a band many years ago called, oh gosh, I forget that. But it was like a song that went like, right about now, funk soul brother, right about, you know the song? Fat Boy Slim? Am I remembering that? That's the name of the band, Fat Boy Slim. Anyway, so check it out now, funk soul brother, check it out now, right? All right, so we're going to check it out. Okay. My video doing it's going to be on YouTube. So what you do is you take the backbone of this molecule and you like crimp it. Okay? Crimp it. You get the jip. Crimp it. Crimp it. So we're going to crimp this backbone like this. So I just took this line and I crimped it. You see what I did? Okay, and now that we have our crimp, okay, now I'm going to add some bonds here. Actually, I can't do this. Well, we'll start with this carbon here. So this is a tetrahedron. Remember, all tetrahedrons have 2 straight lines, a dash and a wedge, right? Your generic structure for a tetrahedron on your sheet there. So I'm going to do something really wacky, and I'm looking upside down, and I'm going to go ahead and draw my tetrahedron upside down. And so that's like a tetrahedron upside down. Can you see how it might be a tetrahedron upside down? Like I said, check it out now. Here's another bent, you got this 2 lines already here, so the next 2 bonds that go on this carbon have to be the dash and the wedge. Okay, so I'm going to go ahead and put a dash and a wedge. to put a dashing wedge on him too because he already has the 2 straight lines. I'm also going to put a dashing wedge on him. And this guy's bent, right? The oxygen's bent. So now we just do, and a hydrogen atom is bent. And that would be the VSEPR sketch for this compound. This compound is called ethanol, by the way. But now the lone pairs are here, but we don't have to draw them, right? That's not necessary for a VSEPR sketch. So going from here to here, what do you think? Kind of crazy, huh? So pump the Fat Boy Slim and then try it, you know, in your own time. I don't remember what the name of the song is, but I love that song. It's kind of a catchy tune, you know. Kind of goes the same thing as like Gangnam Style, you know, like with Psy. I love that song too. It just has like a beat to it, you know. People look at you funny because you're walking down the street with the beat. Anyway, all right. And meanwhile, you're thinking, VSEPR sketch, crimping it. Okay? Crimp the backbone of the molecule, and that gets you on your way to starting to make tetrahedrons. All right, and that's really the goal. Now, on the exam, I'm not going to ask you to draw a big molecule like this. I'll just have you draw single central atom, maybe 1 second inner atom at the most. This is a bit over the top, but I figured I'd show you something that's over the top because it's fun. I don't know. But can you see how you get the tetrahedron shape from all these? You know, so the generic tetrahedron is a dash and a wedge and 2 straight lines. Okay. So this gets me to polarity again. This is actually a slide from chapter 9. Okay, but I'm showing it again because in chapter 9, all we talked about was bond polarity. But now that we've done VSEPR, now that we have shapes to deal with, okay, now we can look at the polarity of molecules, not just the polarity of bonds. Okay, so what's the difference between bond polarity and molecular polarity? Well, with bond polarity, you're just looking at a bond by itself, but I gotta tell you, I don't care about that. Okay, bond polarity bores me to death. Okay, but I teach it because it gets us to what I'm really interested in is molecular polarity. Okay, so why do we care if molecules are polar or not? Because it affects not only the boiling points and melting points and other physical properties of compounds, which again kind of bores me, I'll be honest. But more importantly, what it doesn't bore me on is the solubility of compounds, how we can separate mixtures of compounds, how can we do chromatography, right? And the art of chromatography is what I did for a living in industry. Okay, but we have to talk about molecular polarity to discuss physical properties and melting points, boiling points, and also solubility, right? So, okay, so let's talk about molecular polarity. So molecules are polar when they are asymmetrical. All right, so when you talk about small molecules, we have symmetry. All right, if I took this octahedral compound, would you say it's pretty symmetrical? Yeah, it's got same atoms on this side, same atoms on this side, same atoms on this side. All right, so if you have a central atom and all the other atoms around it are the same, there's a high likelihood that it has a lot of symmetry, and we would say that it's non-polar, right? So polar means asymmetrical. Non-polar means symmetrical. All right. So let me say it again. Non-polar, symmetrical. Polar, asymmetrical, or lack of symmetry. Okay, polar molecules have a dipole moment. Okay, now we talked about bond dipoles, but we also have molecular dipole moments. A lot of the time, they will call them net dipole moments, because what they're saying is that the net direction of the bond dipoles point in a given direction added together. Your textbook does a really good job, actually, of talking about vectors and describing dipole moments. I suggest you read it, just in general. It's a good read on dipole moments. So a dipole moment is when a net negative charge is pointing towards one end of the molecule. And then conversely, the other end of the molecule will be positively charged. Okay. Take HCl. All right, this is a really simple example, but it gets the ball rolling. So here's HCl. This has a dipole moment, all right, or a net dipole moment, as they say. Why is the arrow pointing towards the chlorine? It's more electronegative, right? So the more electronegative atom is always going to pull electrons to it, and so the dipole moments are going to be always pointing towards the higher electronegativity atoms. Is this molecule symmetrical? It's not, right? If I cut this molecule in half, I get a chlorine on this side and a hydrogen on that side. I have low symmetry here. All right, and as a result, if you looked at it as an electron density contour, you would get this situation. And they use these delta plus and delta negative symbols to indicate partial charges at the different ends of the molecule. Okay, so a little squiggly negative, I call it squiggly, but it's really delta negative, and squiggly positive. Okay, what if we looked at carbon dioxide? Okay, carbon dioxide is very symmetrical. Okay, if I cut the molecule in half, I get 2 O atoms on both sides. If I cut the molecule this way, okay, I get half a carbon and half an oxygen on both sides. Right, so high symmetry means you can cut the molecule in a multitude of directions and still get equal halves. All right, so now here's the thing. What are these arrows doing? Why are they pointing towards the oxygens? They're more electronegative. Again, it goes. The arrows always point to the higher electronegativity atoms. But notice how they're pointing in equal and opposite directions. If you added these two vectors together, would you have a net direction? And the answer is no. Right? These two vectors are said to cancel each other out. The bond dipoles are pointing in opposite directions, and they cancel each other out. Is everybody all right with that? High symmetry leads to non-polarity. Conversely, HCl, hydrogen chloride gas, is a lot more likely to condense than a molecule like carbon dioxide, which is very nonpolar and wants to stay as a gas. Okay, so, and if you look at the electron density contour, it's very symmetrical. Do you see any squiggly delta or positive in here? No, because the electrons are not residing more or less in any direction. Right? They're spread out evenly throughout the molecule. So symmetry gives nonpolarity. Okay, there is no net dipole moment in a symmetrical molecule, but in an asymmetrical compound, you have a net dipole moment. You've got squiggly negative and squiggly positive. So going back to the compounds we did with VSEPR, let's determine if they're polar now. You notice since I got these drawn up here already, we can go back to those. So xenon tetrafluoride, is this polar or non-polar? Okay, so taking these atoms off and replacing them with lone pairs. Okay, so I've got xenon and fluorine. Which atom is more electronegative? Yeah, fluorine, right? So the electrons that are shared in this molecule, and even the lone pairs out here and down here, are going to be kind of drawn to the fluorine atoms. But here's the thing, this fluorine atom is opposite of this one. And this fluorine here is opposite of this one. So ultimately, the electrons have nowhere else to go but being pulled in all directions at the same time. And so net-wise, they're just going to stay in place. They're not going to go in any net direction. They're going to stay right here. All right? It's like having 4 gorillas on all 4 ends of the molecule here, all with equal strength, pulling that tug rope. You see, like on Sometimes you have these like nature shows, you see these kids pulling tug rope and they're fighting a giant gorilla, and the gorilla still wins because it's so much stronger than the kids. It's kind of funny, but in this case, there are no kids. It's just all gorillas pulling against each other, okay? All right, it's a tug of war, okay? These atoms are all fighting for their lives for electrons. This fluorine's like, no, I want electrons, I want them. And this one says, no, they're mine. Mine, mine, it has nowhere to go, right? And then these two are the same thing, right? The electrons don't go anywhere, okay? So this has no net dipole moment. It is nonpolar, all right? Now here's the thing. Is a xenon-fluorine bond, is that polar? That is polar, right? I mean, if I look at xenon, the electronegativity for xenon, I believe is, I forget. I gave it to you in the notes from chapter 9. 2.6? Thanks. All right, so 2.6, right? So if I write here 2.6 next to xenon, and fluorine is 4.0, right? If I look at 4.0 minus 2.6, I got an electronegativity difference of 1.4, right? That's a polar bond. But just because a molecule has polar bonds doesn't mean that it's a polar molecule. And this is what I'm trying to get at with the difference between bond polarity and molecular polarity. This molecule has polar bonds, but it's non-polar as a whole because of the symmetry of how all the bonds together are arrayed. Okay. So yeah, sure, you have a bond dipole this way, but you also have one going that way. You also have one going that way, and you also have one going this way. So collectively, I cannot put a big arrow on this molecule in any net direction, right? So we have no polarity here. All right. What about, okay, now we can go back to this one, right? So nitrate. So the problem is asking us, use a VSEPR sketch to determine polarity. So we had a VSEPR sketch for xenon tetrafluoride. It was totally symmetrical, and so we couldn't put an arrow on it in any net direction. I drew the bond dipoles in there, but you're not going to do that. Okay, don't worry about drawing in bond dipoles. You're only going to put in one arrow if a net dipole exists. For nitrate, we know that the Lewis structure, the VSEPR sketch looks like this. Right, and it's got resonance structures and all this stuff. Sure, it's got a double bond on one of them. All right, if I were to draw the VSEPR sketch with the electrons in there, or with the lone pairs, is this polar or non-polar?
Non-polar.
It's non-polar. Why is it non-polar? Yeah, the O's are all in opposite directions, right? So yes, I've got 3.5 here, I've got 3.0 there, I've got 3.5 all around. Some students have asked me in the past, well, what about the double bond? Doesn't that make it asymmetrical? Or is anyone here wondering that? Yeah. But what does this compound have that a lot of compounds don't? It has resonance. And so ultimately, this double bond exists at all three locations at the same time. And so because of this constant rotation, the molecule is always going to be symmetrical, right? Again, high symmetry. So this would be non-polar. What about the next compound? CH2, Cl2? All right, is that compound polar or non-polar? Is it symmetrical or asymmetrical? I've got 3.0 for chlorine here. Alright, so write down the electronegativities in there. Asymmetrical or symmetrical? It's asymmetrical, right? Alright, this one was symmetrical. This one is asymmetrical. So that means this molecule has to be polar. Which way does the dipole moment point towards? It's going to be pointing towards the chlorines. So now I can draw a big arrow with delta signs telling me the direction of the dipole moment. That's this molecule right here. Right. Here are my hydrogens. The greens are my chlorines. Dipole moment points right in between the chlorines. My bond dipoles point right at the chlorines, but collectively they're pointing downward. Okay, I'm going to point my dipole moment at each and every one of you. Okay, and at the camera. Okay, am I doing this? Am I doing this? No. This is just one bond, right? I don't care about bond polarity. I care about molecular polarity. Okay, check it out now. Mr. Fernandez in the house. Oh, okay. I know, I'm sorry, it's corny. All right. What's up, Los Angeles? All right.
Orange County, what are you saying?
What's up, Los Angeles? I'm a Dodger fan. Come on, and a Laker fan. We don't have NBA basketball here in Orange County, so. But Orange County's kind of nicer in many ways. It can be. Okay, but I'm an LA fan. Hi. So, what's up, Orange County? Mike Trout, come play for us. Okay, does everybody get the point now? I'm not pointing the bonds, I'm just pointing in between the bonds, because that's where collectively, that's where the dipole moment is pointing towards. Okay, so here's the thing. If you drew a Lewis structure of this compound, dichloromethane, some people might draw it looking, it might look like this. Right, so if you looked at the Lewis structure, can you tell that it's polar just by looking at this? And you can't. So the moral of the story is draw the Vesper shape. Okay, the Vesper tells you if it's polar or not. Lewis structures do not tell you if it's polar. Okay, so could I have drawn this chlorine down here? Sure. Okay, but does it matter? Really not at all, because again, it's a tetrahedral shape. Okay, I could have drawn this molecule with the chlorines up here instead of having it down here. I could have drawn it like this. Okay, I could have been somebody. No, I could have replaced the hydrogen here with the chlorine. I could have done that. And the arrow would be pointing which way then? All right, if I had it, let's see. This would have been trying to figure out how to get this to turn around. Here it is. So it would have been like this. Right? Right, so which way would the dipole moment point now? It'd be kind of like pointing down into the plane of the board. Really, really hard to draw that on two-dimensional paper, right? So by convention, I always put the chlorines down here just to show it. Okay, but you know, drawing a dipole moment into the plane of the board, that's hard. I don't know how you do it. So if you see me just put in the chlorines on one side of the molecule like that, that's why. Just so I can draw it, you know, in two-dimensional space. All right. What about PCl5? Is that polar? So that's PCl5, is that polar or not polar? Polar. Alright, so here's PCl5. Okay, so here's the shape. Okay, yeah, this chlorine's pulling this way. So this chlorine's pulling that way, and this chlorine's pulling that way. Okay, and these atoms here are equally fighting each other too. So is this symmetrical or not symmetrical? This is very symmetrical, right? Okay, you can't say the dipole moment's pointing this way when this atom here is fighting it. You know, you can't say the dipole moment's pointing this way because this molecule, this atom here is fighting that direction. You can't say the dipole moment points this way because this atom is fighting that direction. Right? All these atoms have a say in the direction of where the electrons go. Right, so it's a even 120-degree angle among all these spots. So it's highly symmetrical.
I have a question. Is that because they're all chlorine?
Is that because they're all?
So that
Yeah, they're all equally spaced around the equatorial rim of the molecule.
So basically, that dipole moment goes through like the most electronegative.
Yeah, so if there were a net dipole moment, it'd have to go through any one of these atoms, but there's too many other atoms fighting them. I mean, so yeah, there's bond dipoles, but they cannot hold the other electrons with them because the other atoms are fighting in equal directions. Yes?
But in the other case, it just depends, like, you guys could say that if there's different elements being
Yeah. So all of these are the same, but if we replaced one of these with some other atom, then it would make the molecule polar.
Okay.
All right, now you're introducing asymmetry. Yeah, because right now I've got 3.0s all around. I think phosphorus was what, 2.5 or something like that. Anyway, so because the 3.0s are all around, you know, it's symmetrical. So this is going to be non-polar. Because again, it is symmetrical. So if you think about how many apps do you download to your phone? A, polar, right? App. Okay. SN, I don't know about that, but if you just remember, you know, app like a computer app, right? Asymmetrical, polar. All right, just remember, if you remember that, then by elimination you'll remember non-polar and symmetrical, you know, the other way.